So we're at the point in our course where we're going to look at some physics concepts. Now, for some of you, that may make you a little bit nervous. I don't want you to be scared of it. I don't want you to feel nervous about it. I want you to just think this is going to be about the same level as high school for most of it, okay? I'm going to try and make sure there's some good think and apply questions, so it won't all be math. So you'll have about 50-50. Most of the math is going to be pretty straightforward, but it's going to be thinking about things like speed. You know what speed is. Acceleration, you already know what that is. We're going to talk about force. So that's a push or a pull. And we're also going to talk about work. So these are the four things that we're going to discuss as we look at our physics. And it's going to let us talk about how machines work and how mechanics work a little bit. So today's lesson, we're going to look at speed. The next lesson, we're going to look at acceleration, and then we'll do force. I'm hoping we'll get have those three lessons for you for before break, though it may take us till after reading week in order to get our forces finished up. Okay, so this lesson is going to focus on speed. Now, why do we need to start with speed? Well, these are the four equations that we're going to look at. I'll say the four physics equations. There'll be some other equations that come into play, but equations you already know, like circumference of a circle. That's an equation we're going to use today. It's not a physics equation, but it's an equation we would use to find distance. So there's equations that you already know that are going to help us out today. My question looking at these ones is, how are all these equations related? So let's look down through them. So speed is distance over time. Notice acceleration. This little triangle means change in. Acceleration is change in speed divided by time. So in order to talk about acceleration, we have to know what speed is. How does changing speed affect acceleration? Well, the greater the change in my speed over a time, the greater the acceleration. So speed and acceleration are connected. Then let's look at the equation for force. Force is mass, how big something is, times its acceleration. So how fast I want to move something is controlled by acceleration. The push I need to move it is force. So you see, they build on each other. So that's why we're going to cover all of them. And the very last thing we'll look at, we're going to look at work. And work is force times distance. If you think that sounds familiar to maybe a torque equation you've talked about before in maybe your course with Jeff, I'm not sure if he's got to talking about torque or not, but that is an equation we also use for torque. All right, so those are the four key equations we're going to look at. And we're not going to use all of them today. In this lesson, we're going to look just at the equation for speed. So what is speed? Speed is the distance distance moved per unit time. You will find that sometimes instead of using the word speed, we use the word velocity. Velocity and speed are very similar. In physics, they have slightly different definitions. Speed is just the total distance of a trip divided by how long it took. The total distance moved. Doesn't matter if it was left, you went left and then right and came back to where you started. So your overall distance from your starting point was 0. It doesn't matter. It's the total distance you moved divided by the time. There's another physics term we use, it's called velocity. We're not going to use that term too much. You will see it in the acceleration slides. But the word velocity just is speed, including what directions we went. So if I was talking about a velocity, if I went to Charlotte, left campus, went to Charlottetown, and then came back to campus, because I went opposite directions, the directions would cancel each other out. So if the physics term would say I went 0 kilometers per hour, but speed goes, wait a second, you put kilometers on your car, that's why we call it a speedometer, you went a speed, an average speed getting there and back. So those are two terms that we use sometimes. I don't want you to worry too much about velocity, but I am going to I just wanted you to hear the word because we will see it again, but we're going to use, instead of using the word velocity, we're really going to use the word speed in our course, if you've had a physics course before. you will notice times where the word velocity could be used and direction could be used. But I know we're just going to use the word speed for the sake of simplicity. So hopefully you've had physics. You can forgive me for sticking with the simplest definitions that we need for our purposes. So the equation for speed is distance divided by time. We can put that in a triangle form. Now, you know, from a math perspective, I don't love the triangle form, but it does work and it does save some rearranging for us. Now, you used the triangle before. So if I want to find speed, I cover speed up and I get distance divided by time. If I want to know the time it takes to get somewheres at a given speed, I would cover time up. And time is found by taking distance and dividing by speed. And if I want to know how far I've traveled, I'd cover the D up, and it's speed times time. Now, what units do we measure things in? Distance is going to be measured in meters, miles, or kilometers, depending on the question. In physics, we often use meters. Meters, seconds, and meters per second are what we call the SI units. They're the scientific units for measuring speed, distance, and time in. But in the real world scenario, we're often going to use kilometers, hours, and kilometers per hour. Or if I was an American, I would use miles per hour, and hours, of course. Time, fortunately, is the same here as in the US. Some people might argue time feels a lot longer there, especially depending on what political stuff's going on. But we both measure in hours. Thank goodness we measure time the same. That would really cause some trouble. But we have meters, miles, or kilometers for distance. And then your speeds will be kilometers per hour, mph for miles per hour, or meters per second, depending on the question. One thing I will tell you is if a question asks you, find the speed in kilometers per hour, check and see was the distance given in kilometers? If not, put it in kilometers first. If you want to know kilometers per hour and they gave you minutes for the time, turn the minutes into hours. You'll never see kilometers per minute. It's just, nobody uses that. Turn the minutes into hours and then do your calculation. So we're going to do just a couple example questions. The example questions, math is pretty easy for them. You may want to draw a triangle so that you can follow your math there. I'll write the equation out each time. A car travels 456 kilometers in 4 hours and 25 minutes. What was the average speed of the vehicle in kilometers per hour? So I know my distance is equal to 456. I know my time is 4 hours and 25 minutes. I need that all in hours. So how do I get it all in hours? Well, 25 minutes is close to half an hour. So I take 25 minutes and I divide it by 60 minutes per hour. I don't like that. And that looks like miles per hour. We'll divide it by 60. I'll just leave it like that. Divide it by 60 and we get 0.42 hours. It's close to half, so that makes sense logically. So we have 4.42 hours. Now we need our equation. Speed is equal to distance divided by time, which is equal to 456 kilometers divided by 4.42 hours. Notice it's kilometers divided by hour, and over here it was kilometers divided by hour. The units have been matched, which gives us 103 kilometers per hour. It's a nice, easy calculation. The next one we're going to look at. The average speed limit on PEI is 70 kilometers per hour. I think that's actually a pretty accurate number. If you're traveling from Surrey to Tignish, so that's 215 kilometers, how long will it take? So we want to find how long. We know we have a speed of 70. We have a distance equal to 215. And I want to know what is the time. So using our equation, speed is equal to distance over time. Now, if you use your triangle to rearrange, you will find that time is equal to distance divided by speed. You could also set it up like cross multiplying in order to figure that out, depending on which way. Maybe I should walk you through rearranging that. I think I will. Let me I'll walk you through rearranging it just for the sake of practicing some algebra. So what we want to do is I want to get time alone, but time is on the bottom. When time's on the bottom, we have to get rid of the fraction first. So we multiply both sides by t. That cancels out. So now we have time times speed is equal to distance. I need to move speed, so I divide both sides by s. So time is equal to distance divided by speed. So it's not too bad to rearrange, but that's how you would rearrange it. Now let's plug in the values. Time is equal to our distance of 215 kilometers divided by 70 kilometers per hour. Notice kilometers and kilometers. We have hours in for time, so we will get hours out for time. And you will get 3.1 hours. Now, if you wanted to turn that into hours and minutes, you would take 0.1 hours times 60 minutes gives you 6 minutes. So you'd have 3 hours and 6 minutes to drive. That's how long it would take. Nice, easy calculation. Let's look at the next one. A Honda Civic completes a quarter mile in 12.7 seconds. How fast is the car traveling in meters per second? This one, you have miles, seconds, meters per second, and a conversion that has miles and kilometers. We got conversions. Okay, so this is a good conversion practice. So a quarter mile. Quarter mile, well, it says 1 mile is 1.6 kilometers. So a quarter mile times 1.6 will give us how many kilometers? And we get 0.4 kilometers. There's 1,000 kilometers in 1,000 meters in a kilometer. So we multiply by 1,000 and we get 400 meters. So quarter mile is 400 meters. I want to know how fast is the car traveling. So there's our distance. Time is 12.7. You notice it was in seconds. Would it make sense to put this in kilometers per hour? We're going a short distance in a short time. It makes more sense for us to describe our speed in meters per second. So speed is equal to distance over time, which is equal to 400 divided by 12.7 equals 31.5 meters per second. And that will be our speed. That is approximately, it's just over 100. It's somewhere around maybe 115, something like that. Well, when we do acceleration, I'm going to look at it. We'll do the conversion for that. All right. Classic think and apply. I love putting think and apply questions in because it gives you a math break. So you just did some math, pretty easy calculations. Now I want you to think about the math. So speed is equal to distance divided by time. That's going to be important to remember answering this question. When racing, why do vehicles try to get on the inside of a corner to turn rather than the outside? Okay, you're driving a car. While you're on the track moving, can you change the maximum speed that car will travel at? Not typically. Everything is already set up. And as far as that goes, the vehicles have a maximum speed they can reach, especially you can modify within a particular weight class, but eventually you'll hit a maximum. So if you can't change how fast a car can drive, what else can you change in order to change the time it takes you to finish a lap? Well, if we look at our equation, speed is equal to distance divided by time. If I want to make my time as small as possible, I need to make my speed as large as possible. We just said, oh, we can't change that. So what can we change? If I can't change the speed, if I can make the distance I go shorter, I'll get there in less time. Okay? So let's think about a vehicle driving around this track. These cars are coming down the track. If they stay on the outside edge, The distance they travel will be longer or shorter than if they move to the inside edge. Well, you can tell the inside of the circle is a whole lot shorter than the outside. So when trying to pass, they get on the inside corner whenever they're going on around corners. Now we don't have a lot of passing lanes on PEI that have corners, but there's one thing I always notice when I'm driving in Nova Scotia. It has been well over a year since I've been over there, and perhaps we won't say homesick, but I'm missing the mainland a little bit some days. But when you're driving down the highway, there are some places where you've got your 2 lanes. In Halifax, there's one spot, it's a 3-lane section, and you're coming out and it's a fairly sharp corner. And I always like to make sure I'm in the middle, especially if it's on the inside of the corner, especially if it's busy traffic, because it's much easier to pass people, much easier to get through the traffic that way, just because it's a shorter distance. You can actually get ahead a few cars without actually changing your speed. Okay, so when racing, why do they do it? Well, in order to make their race shorter in terms of time, they have to make the track shorter, and the shortest track distance would be if they followed on the inside the whole way through. Now, they don't follow on the inside the whole way because it makes such a tight corner, and the corner is really tight, it can make it hard to maintain control. So you'll see they make the corner a little bit wider, but they still shorten it up nice and close here as they make their corner. So one of those cool little things. I guarantee there's going to be some folks in the class that like going out for a drive somewhere and hitting some good corners. I've heard my husband say that numerous times about taking a ride on his bike. He likes finding a spot with good corners. So you can feel the pull that you get as you go around the corner. And that's one of those things you think about is speed, just how speed, distance, and time impact your going around, how quickly you make it around the corner. Okay. We don't necessarily do the math on it, but we use the logic. Okay. I am going to get you to do a calculation. We're going to prove how much faster you would have to travel if you were on the inside of the track or the outside of the track. This picture I don't think is drawn to the right scale for the measurements I'm going to give. Maybe the last one was closer. So a car travels the inside of a hairpin turn. So a hairpin turn is just a U-shaped turn. Okay, so we're just looking at this U-shaped turn. So one car travels along the inside of the turn. The other one travels along the outside of the turn. Okay. If the car is traveling 27 meters per second, how long will it take to make the 180-degree turn? So that's part one. That's the car on the inside. Then I want to know how many meters per second, what speed would a car need to travel if it was going around the outside of the turn? So imagine you and your friend are, I don't recommend doing this, just so you know, but I think most of the roundabout up at the corner here in Summerside, right by Superstore, the top of Granville Street, I think there's 2 lanes the entire way through. So it's like you guys are halfway through the turn and you're going to see who's going to have to drive fastest. If you both enter the roundabout at the same time, who would have to drive fastest, the person on the inside or the person on the outside, in order for you to both exit the roundabout at the same time? Now, there is a question that's like that on the quiz. So the question that's like that on the quiz, I want you to think back to this example. Come back to it if you need to. Now, in this example, we're only doing a half circle. If you were doing a roundabout, you do a full circle. So you can keep that in mind. There's my little tip. So what do we need to do? So for the first question, we'll call this 1. So this is the inside car. Well, we know it has a speed of 27 meters per second. That's around 90. And I want to find time. And speed is related to distance and time. So, well, how far is this car traveling? We need to calculate it. So that's our first thing. We're going to find distance. This car travels half a circle. So the distance traveled is the circumference of a circle, which is 2 pi car, but it's divided by 2 because it goes around a half a circle. So 2 pi r, which 2 and 2, half a circle, we're going to end up with just pi times the radius. They cancel out. So the distance this car drives is pi times 3.5, which gives us a distance of 11 meters. Now let's look at our equation. Speed equals distance over time. I want to find time. Speed and time are going to switch spots. So we're going to have, or you use your triangle if you want. If you're using your triangle, it'll be speed, time, and distance. So I want to find time. It's going to be distance divided by speed, which is equal to distance of 11 meters divided by how fast it was traveling, which is 27 meters per second. Well, how long did it take to complete the turn? Less than a second, that's for sure. 0.407 seconds. So that's flying around that corner. It's a pretty tight corner and it's really moving. 27 meters per second would be somewhere around 90 kilometers per hour, give or take. Okay, so we know how long it took. So it took 0.407 seconds. We're going to keep 3 decimal places because if you're racing, that 3rd decimal place is going to matter. 2. How many meters per second, so what's the speed, would a car need to travel on the outside of the turn? So outside edge, and the outside radius is 5.8 meters to make the turn in the same amount of time. So we're going to have to find the distance again. How long is the outside curve? So the distance is going to be same formula as before, pi times radius, which is equal to pi times 5.8 meters, gives us a distance of 18.2 meters. It's quite a bit more distance. It's not quite double, but getting close. Time, well, they've got to both do the corner in the same amount of time. So 0.407 seconds. So how fast is the second car? So distance divided by time equals 18.2 meters divided by 0.407 is equal to how many meters per second? If I put this in my calculator, right? 44.8 meters per second. Now, you could do a conversion on that. If you wanted to figure out how many kilometers per hour, you can do a check on this. To switch it to kilometers per hour, so 1 kilometer per hour is equal to 3.6 meters per second. Okay, 1 kilometer per hour is equal to 3.6 meters per second. So if I wanted to switch this into how many, actually, I have that written backwards. It's the right number, but I have it written backwards. I was thinking, if you're wondering why I was pausing, I was thinking as I wrote it, which way it goes. So 3.6 kilometers per hour are in 1 meter per second. Okay, so if I would take 1 meter per second, and I multiply, if I take 44.8 meters per second and I multiply it by 3.6, whoops, you would get 160 kilometers an hour is what you have to do the turn at in order to match the guy on the inside. The guy on the inside at 27 meters per second, 27 times 3.6 is 97 kilometers an hour. So 97 kilometers an hour for the corner versus 160. I think I'll take the corner slower, but maybe a little sharper. So that's just some of those things that would come into play if you were dealing with racing on a track that had corners. You may also think about it a little bit when you're driving, but please drive safely, be smart. All right, I have another think and apply question. And of course, we're going to do a math equation to talk about this one as well. And there are a couple questions, at least one question in SAM that gets you to think about this one. How will installing a smaller tire change your vehicle speed? Now, where does this question come from? This question comes from personal experience. We have a Pathfinder. It uses 18-inch rims, and I forget the sidewall height. Oftentimes in the winter, they will put smaller tires on, maybe a 17-inch, but they put a tire that has a higher sidewall. Well, we needed winter tires, and instead of buying the new winters for it that were 18s, we got tires on rims that were off a Rogue. They both fit, but the tire was a teeny bit smaller. How did it impact my speed? Did that mean while I was driving, my actual speed was more or less than the speedometer reading? I always noticed it every time I came up to one of those flashing lights that tells you what speed you're going. So we're going to work at a calculation. We're going to figure out what would happen. So you can probably tell we've gone from day to night in the video here. So it's been a few minutes, half an hour since I was last recording. So hopefully I kind of remember where we took off. So we were looking at how will installing a smaller tire change your vehicle speed? Will the speedometer be read higher or lower? So if you look at the two tires, which tire has the larger circumference? The bigger tire has the larger circumference. It's got a larger distance around the outside. So every turn, it will move further than the little tire. So if I install a small tire, trying to get my tablet to turn on, if I install a smaller tire on my car than it's intended to have, and the sidewall height makes it such that the total circumference is smaller, every time my wheels turn, I'm not moving as far. Now, if you look at our equation for speed, trying to get a connection here. Just bear with me for a minute. So if we look at our equation for speed, speed is equal to distance divided by time. So if I move a shorter distance, if the distance decreases, it means my speed will decrease. So my speedometer, if my speed with the small tire, I'll have less speed with a little tire than I do with the big tire. Because of that, my speedometer will read higher than my actual vehicle speed, because every turn I'm not going to be going quite as far. So my speedometer thinks I'm driving with a bigger tire, so it thinks I'm actually moving faster than I really am. It thinks I'm covering more distance than I really am. So I actually would drive slower. Now that's one of the things that I noticed when we were driving the Pathfinders. Every time we'd come up to one of those sensors that tells you how fast you're going, I would notice that whenever I had a smaller tire on, the speed would register, and these tire sizes that we're going to actually calculate, the speed would register between 5 and 10 kilometers lower than what the speedometer in the car was saying. So we're actually going to do a calculation, and we're going to figure out, well, what is the actual difference in speed at 90 kilometers an hour? Okay, so it's not really difficult to figure out. One of the things we need to figure out, though, is what is the change in distance, or what's the distance that each wheel travels? So in order to do that, we need to review some old math. Old math says you need to calculate circumference. Now, you know how to calculate circumference. You've done that before. But we have to do it from a tire ratio, and we haven't done that in math, but we may have talked about it with Jeff. Tire sizes are marked with 3 numbers. You have the width in millimeters, followed by the height. The height is always given to you as a percentage, and it's a percent of the width. So we've got some stuff from last semester coming up. And then the last number is always your rim diameter in inches. So you've got width in millimeters, rim diameter in inches, and percentage in the middle. This is a great math question to review, percentage and conversions. So I'm going to find out the circumference of this tire in millimeters. The reason I wanted in millimeters is we're going to do our comparison in meters. So if I have millimeters, it's going to make meters easier to get to. So the first thing I need to find out is, what is the sidewall height? Well, the sidewall height is 60% of 225 millimeters. So I take 225 millimeters, I take my width, and I multiply it by 0.6. Doing that, I get a sidewall height of 135 millimeters. So this is 135, and this is 135. In the middle, I need to figure out, well, what's this distance? Okay, so to find out that distance, it's my rim diameter. Well, we know the rim diameter, and we often abbreviate diameter as DIA. The rim diameter is 17 inches. How do I convert that to millimeters? Well, there's 25.4 millimeters in an inch, so I multiply by 25.4. You could use your conversion chart to check, and you will find that it's 431.8 millimeters. So the total height of the tire is going to be equal to 2 times 135 plus 431.8, which gives me 702 millimeters. Next, I need circumference. So one of the ways to find circumference is pi times the diameter. Or you could do 2 pi times the radius. You just have to make sure you calculate radius first. But pi times the diameter would give us pi times 702 millimeters will give us 2,205 millimeters, which is approximately 2.2 meters. So every turn of that 17-inch tire, I'm going to go 2.2 meters. That's my little tire. What about the larger tire? Well, we have exactly the same math. So you know how to do it already. You should be able to calculate this one on your own. First thing we're going to do is find the sidewall height. So the sidewall height is going to be 235 times 0.65, which gives us a sidewall height equal to 153 millimeters. Then we're going to figure out the rim diameter. And the rim diameter is 18 times 25.4, which gives us 457 millimeters. So the full tire diameter is equal to 2 sidewalls, so 2 times 153 plus 457 gives us 763 millimeters. So it's about 60 millimeters taller. That's going to be close, just about 2.5 inches taller. What does that make us for difference in circumference? The circumference is going to be equal to 763 times pi, which is equal to 2,397 millimeters. And to round off to one decimal place, like in the last question for meters, would be about 2.4 meters. So every turn of the tires, you are moving 20 centimeters further if you have a big tire arm and a little one. 20 centimeters, multiply that by 10. So in 10 rotations, you've gone 2 meters. In 1,000 rotations, you've gone 0.2 kilometers. Think about how many times the vehicle's tires rotate. You got a lot of rotation, so it's going to make a fairly good difference in speed. Let's figure out what the difference is in speed. So in this case, the stock car has has tires at 225, 60, 17. This is actually the tire specs for standard for a Rogue. I forget what year, you'll have to bear with me. So we just calculated, if you need to look back, we just calculated the size of this tire. And we found that it has a circumference. The circumference is equal to 2.2 meters. We found out that the bigger tire has a circumference of 2.4 meters. Okay, so what we're doing is we've got the stock tire and we're switching and we're putting a larger 18-inch tire on. What will the actual speed of the vehicle be when the speedometer says 90? Well, let's look at our equation. Speed is equal to distance over time. Let's look at what's actually changing in this equation, and we can actually simplify the math. Is speed changing? Well, yeah, we know it's changing because the tire's traveling a different distance. So the speed is changing. And I just said the tire's traveling a different distance. So as distance is changing, time, the amount of time I'm traveling stays the same. So let's do a rearranging. Time is equal to distance divided by speed. So the time with the little tire equals that. The time with the big tire, if these two are equal, then the two fractions are equal. Would you agree? Has to be. It just makes a ratio. So the distance one would be the tire size divided by speed. It's going to be equal to the second tire size divided by the second speed. So let's figure out what's the difference in speed. If we put a bigger tire on, the car should go faster. So we're going to find out if that's true. So 2.2 is the tire size. That's the distance that tire travels, divided by the speed. So the tire size to speed ratio. Whoops. Yeah. Sorry, the speed goes with the little tire. Double checking. And then distance too is 2.4 meters. And it's going to be X kilometers per hour. Just what this did. Now, you might wonder, why in the world did she rearrange and make the two equations equal to each other? The reason I did that is it saves us doing some conversions. Otherwise, you change your meters to kilometer, figure out the time, and then calculate again. This is actually much faster. Now, it is a bit of a math trick that a lot of people wouldn't think to do, but that's okay. You don't necessarily have to do all the tricks in one question. So now we cross multiply and divide. So you'll do 90 times 2.4 divided by 2.2. And you will find that the speed is equal to 98 kilometers per hour. So the 8 kilometers per hour slower that I was seeing when I switched to smaller tires actually is true, because if you took a Rogue and you put my big tires on, it would be 8 kilometers an hour faster. Okay? So we can actually prove it using simple speed equations. So in summary, going to have a few equations to calculate in SAM. You won't have one quite like changing tire size, but you may have a question that asks you to apply and think what would happen to the speed if you change the tire size. Keep that in mind. Come back and check if you need to. But when you're doing calculations, check and see if you should do any conversions. What units should the answers be in? So check what you want for an answer and switch. If you want kilometers per hour and you're given how many minutes you've traveled, switch the minutes to hours first. And then sometimes you might need to do other calculations to find the distance traveled. So for example, if you're going around a track, you'd need to know how long is the track. So you might be told enough information to find out how long the track is, just like we found out going around that hairpin turn, went around a half a circle. So we had to figure out, well, what was actually the distance in half a circle? So you're bringing in that math from last semester. That's why last semester was important to make sure everybody had. And then you've got your equation here. You can either use your triangle form or you can use this equation form and rearrange it. And that finishes off our little section on speed.